thesis defense. We'll begin with a presentation of approximately an hour, hopefully no longer. And at the end of, probably, unless you have a desperate question about notation you don't understand, maybe hold questions to the end, and then please feel free to ask Logan some questions about what he's been up to over the last few years, and then after that we'll ask you guys to leave, and we'll have a discussion. So Logan, please take it away.
Before you start, could the committee members raise your hands? Making sure you're all here.
All right, thanks a lot, everybody, for coming. Presumably I need no introduction since the room is full. But I've been at MSU for around 6 years, been working on my research for something closer to 4.5, with Neil and Nico very closely here at XGI, and more recently with Steve Taylor and Sarah Vigeland, who are some postdoctoral collaborators that I have at Nanograv, which is the North American Pulsar Timing Array. And what I'll be talking about is the detection prospects of exotic polarizations of gravitational waves not allowed in Einstein's theory, using low-frequency gravitational waves, which are two methods: a more established method, pulsar timing, and astrometry, which is the newer method. So without further ado, let's just dive right into it. So why do we even bother testing general relativity? Because up to this point, we have some pretty convincing evidence that Einstein's theory is correct. First and foremost, it's not a quantized theory. And a whole bunch of the best discoveries in physics in the 20th century were because of the power of quantum theory. And the fact that these two theories don't get along very well is a really, really big deal. General relativity also admits singularities at the centers of black holes and also the beginning of the universe, which is a really bad thing, because there's no way to describe physics whenever things go to infinity. There also are some mild disagreements from cosmological observations and observations of galactic velocity curves, but it might not be GR's fault. The form of the equations might still be correct, and we just haven't accounted for various other kinds of exotic matter that we just don't encounter all that often here on Earth or in laboratories. So it just depends on what school of thought you adhere to. You can invoke a special kind of matter and fix things, or you can change the theory and fix things. But if you're going the latter route, typically an alternative theory of gravity will admit alternative polarizations that are not allowed in Einstein's theory. And if we were able to detect any of these alternative polarizations, that would be the smoking gun evidence that Einstein's theory specifically is incomplete, as opposed to invoking some new form of matter. So here's a little roadmap for what I'm going to be discussing today. I'm going to review what a pulsar timing array is and the geometry, the general geometry of alternative gravitational wave polarizations. I'm going to introduce the case of continuous gravitational waves, which is to say we have a really loud black hole binary that's close to us, and that's why we can detect it. What that looks like in alternative gravity using a pulsar timing array. I'm going to expand off of all the properties that I introduced here and talk about the more likely case, which is detecting what's called a stochastic background of gravitational waves. And we find that for some of the alternative polarizations in this case, for this source, the properties, geometric properties of each polarization affect the signal-to-noise ratio, and that makes it significantly harder to detect some of these alternative polarizations in this context. And then I'll briefly introduce astrometry and make some analogies about what make it similar to pulsar timing and how some of our discoveries were reinforced with this particular new method. Quick little outline of my publications. So chapter 3 was whenever it was my first project, and we published a PRL, physical review letter, which is kind of a bigger deal to publish because it's meant to be read by non-specialists and highlight some of the main takeaways of the research. Chapter 4 was published last year in Ph.D., and then we recently submitted the continuous wave case for alternative gravity just last week. And there will be more papers coming out because this formalism, this method, is going to be applied by all subsequent nanograv data releases. So that'll be good for me.